Motricité Interaction Performance Laboratory, Marc. Professor Marc Latash is an eminent researcher in motor control and muscular coordination of human movements, and author of reference book has Control Human Movements, the Neurophysiological Basis of Movement, Synergy, and recently Fundamental of Motor Control. He has published over 300 papers in referred journals. Thank you for your visit at Nantes, and I'm sure your conference will be fascinating.
Well, thank you very much. Right, it's a great pleasure to be here. Thanks for inviting me and treating me to a great lunch. Great, I mean, the food was so good that if I start falling asleep, please wake me up. Here is my plan for today. I'm going to try to introduce to you a certain philosophical view on how I think human movements should be studied, and then introduce some operational definitions for things that we measure, explain how we measure them, and then show how this can be applied to certain studies. And well, it's not my choice, it's the choice of people who invited me to illustrate with two examples. One of them is effects of fatigue, and the other one is anticipatory control of posture. So seemingly two completely disjointed topics, I'll try to merge them somehow together, and by the end I'll try to also introduce a general physiological framework within which everything fits together, if I have enough time. Now, this is a very large program, so typically it would take me 2 seminars to do it. So I'm sorry that it may take more than your traditional 45 minutes or 1 hour. Also, please interrupt me if you have questions at any moment. You can raise your hand or can just shout from your spot. Because I'd rather be interrupted. I like being interrupted, frankly speaking, because it's becoming much more lively. Okay, so before I forget, because sometimes I do forget, I want to pay respect to my colleagues, students, postdocs who participated in different projects there. And Gregor Schön and John Scholz are two very close friends with whom we worked on the uncontrolled manifold ideas. Then I'm going to talk about some examples of multi-finger synergies. And there is Andrei Smilga, who is a professor at the University of Nantes, but in theoretical physics. But, well, he's not here, but I hope that he may emerge at any moment. And Frédéric Dagnon, who is now in Marseille, and he was a postdoc in our group. Studies in multi-muscle synergies, Thomas Robert, who is also from France. Actually, if you take a look at all these names, you will have a completely wrong impression on the names in the United States of America. Because among those here, there is only one American, John Scholz. It so happens that in our group and in our lab, I don't know why, we don't discriminate against Americans, but somehow we don't get too many of those. But we have a lot of Indians, Chinese, Koreans, and so forth, and French, by the way. Okay, so I want to start from the very first definition. Now, what is the field of study? My field of study is motor control. So I want to define it explicitly. So for me, motor control is a field of physics, a field of natural science. And into physics I put together chemistry and physiology, everything is physics. So everything that follows laws of nature. And it's an area of physics exploring how our central nervous system interacts with the body and with the environment to produce purposeful movements. So motor control for me is definitely not a subfield of control theory or engineering. And so you are not going to hear anything like internal models and words like that from me, because I think they're irrelevant to motor control. These are very nice words for the control of ballistic missiles or robots, but not of the human body, or not even of something smaller than the human body. Much of the talk is going to be about the problem of the motor redundancy. So this problem was, in most minds, is associated with Nikolai Bernstein, who was a great scientist, a physician by training, but then self-taught mathematician, who introduced many or formulated many problems in the field of motor control. So the problem of motor redundancy basically is that at any level of the description of our system for movement production, there are more elements or more variables that the elements produce than the number of constraints typically associated with the task. Now, Bernstein used a kinematic example. So when I point at the tip of my nose, the coordinates of the tip of my nose for the hand, they define three numbers, three coordinates in the three-dimensional space where we happen to live. But the number of joint rotations is way larger than 3. Even if you don't count the joints of the hand, there are at least 7 major joint rotations. And you don't count the scapular motion, there are at least 7 major joint rotations. So in a way, if I want to define a joint configuration that solves this task, I have to solve 3 equations with 7 unknowns, and which is obviously impossible to do. So there are 2 approaches to that. Bernstein himself formulated this problem as the problem of elimination of redundant degrees of freedom. So he thought that the central nervous system, the brain, somehow gets missing equations or uses some other method, for example, optimization, finding an optimum of some kind of a cost function to define a perfect coordination, a perfect combination of joint rotations that would solve the task. And the field of motor control has been under the spell of this formulation for many, many years. And so people address the problem of motor redundancy using mostly optimization techniques. Now, it doesn't happen only at the level of joint rotations. Like every joint, even the relatively simple elbow joint, which has only 1 kinematic degree of freedom, is crossed by multiple muscles, 6 muscles, for example, crossing the elbow joint. So one can ask a question, what kind of muscle forces should one produce to get a certain net torque in the joint? It's another problem of motor redundancy. There is only 1 equation with, for example, 6 unknowns. And one can go down and ask a question, what motor units and at what frequencies should one recruit in order to get to match a certain level of muscle activation? Well, this is 1 equation with hundreds of unknowns, and so forth. So at any level of description of the system for movement production, you always encounter this problem of motor redundancy. So the alternative is, and that's the approach that we try to develop in our group, is the solution of motor abundance. It's kind of a play with words, redundancy and abundance. Redundancy means something extra, something additional that you want to get rid of. You want to put under control, while abundance is something that you enjoy. It's also extra things, but you enjoy, you don't want to get rid of that. So the idea is that this typical excess of those variables that the elements produce, I'm going to call them elemental variables, it's not a computational problem for the system. It's actually a rich apparatus that allows the system to combine stable performance and also quickly changing performance, flexible performance, so adaptable performance. And we think that this is done by neural circuits that lead to certain signatures of movements, which I'm going to call synergies. Now, the word synergy has been in the field for a long period of time, so I'm going to define it in a minute. But first, I want to remind you of a study that Bernstein ran, well, nearly 100 years ago, actually 90 years ago. Now, I couldn't find on internet a picture of a blacksmith. So that was the closest I could find. Bernstein ran this study on professional blacksmiths, so people who did this movement, hitting the chisel in one hand with a hammer in the other hand, like 1,000 times a day for years. So they were absolutely best trained subjects you can imagine for this experiment. And he recorded with his Stone Age Optotrack, he recorded the trajectories of the important joints, important markers that he placed on the bodies of his subjects. And he discovered the following, that the variability of the tip of the hammer was smaller than the variability of joint rotations. And let's now not ask a question how he compared the two. He actually did it wrongly, but he got the right conclusion based on wrong analysis of the data. Because obviously variability of joint rotations is measured in radians or radians squared, while variability of the tip of the hammer is measured in centimeters or centimeters squared or meters squared. So these are incommensurate units unless you somehow build a model that links them together, and he didn't do that. But he got the right, intuitively he got the right answer. So he asked a question, how can it be? Obviously, the brain cannot send signals to the hammer. It can only send signals to muscles. Muscles produce joint rotations. They don't move the hammer directly. So how can it be that the signals from the brain produce noisy joint rotations, but invariant trajectory of the tip of the hammer to which they have no access? It's a very good question. He didn't somehow develop this thinking, otherwise we would have probably gotten this so-called uncontrolled manifold hypothesis like 70 years earlier. But he did use the word multi-joint synergy in order to describe this coordinated action of individual joints in such a way that they correct each other errors. So one can have this basic result only in one case if an error in one joint is corrected by another deviation in another joint or in other joints. And this cannot be based on detecting the error and using feedback loops to correct it, because the movement is too fast. It doesn't allow for feedback-based correction. So it should be basically a feed-forward system which doesn't use sensory corrections, ensuring this type of performance. So let's get to the notion of synergy. Now, this is a very common definition of synergy, which is used in our field, that its patterns of variables can be kinematic, kinetic, electromagnetic, that are reproduced or scaled in parallel over the time course of an action and or across repetitive trials. And people use principal component analysis or other types of matrix vectorization techniques to identify and quantify those synergies. I personally don't like this definition, and I'll explain you why. Imagine that you have a chair, and you put four force sensors under the four legs of the chair, and then you ask people with different weight to sit on that chair. The forces under the four legs will scale together very nicely. So if you run then any kind of principal component analysis, you will find one principal component accounting for 99% of the data. But I don't want to call the chair a synergy of its legs, because it makes no sense to me. Because you can run this experiment without a chair but with a stone, and putting four force sensors under four protrusions of the stone and asking people to sit on it. So to me, this parallel scaling of signals may reflect simply the structure of the object that you are studying, not any kind of control, not any kind of task-specific behavior. But I think if we want the word synergy to have any biological meaning, we have to define it in a biologically sensible way, so that it reflects specificity of behavior of biological objects as compared with inanimate objects. So I'm going to offer an alternative definition. I'm going to stick to it. So in this definition, all the words are important. So synergy is a task-specific correlation of elemental variables with the purpose to stabilize the performance variable. Synergy is task-specific. This means that you have a bunch of elemental variables, but different tasks. You can build different synergies based on the same elements. You cannot do it with the legs of the chair. They can do only one thing, support the weight that's placed on top of it. It is covariation, which means that if one elemental variable deviates from its average behavior or preferred behavior, others will also deviate in a lawful way, so they will covary. It has a purpose, which means that synergies do something. For example, the phrase, "the human fingers are a synergy," is meaningless. The phrase, "the human fingers are a synergy stabilizing grip force," is meaningful. It can be tested in an experiment. And the purpose, what I suggest, is in ensuring certain stability properties of the action. So stability properties of performance variables. I'm going to use my standard illustration to simply show you what I mean under the synergy, because these are just words, and I'm going to use a mental experiment. So imagine the following, that I ask you to press on two force sensors with two index fingers and to match a certain level of total force, for example 20 newtons. It's a very easy task, so if I'm not telling you how to press with each finger, just in a natural way. And after, I don't know, after 30 seconds of practice, anybody can do it. It's a very easy task. Then I ask you to do it 100 times in a row, and I record forces produced by individual fingers. What kind of a data distribution am I going to observe? What kind of a cloud of data points? So for each trial, I'm going to plot force of one finger against force of the other finger on this picture. Now, this is the minimalistically redundant system. It has two elemental variables and one constraint associated with the task, so it is redundant. And it's one of the very few situations when I can actually draw on the two-dimensional screen what can happen, because in future I'm going to talk about multi-dimensional spaces, then I cannot draw on the picture. I plot here two lines. Now on the one hand there is force 1 versus force 2, this natural system of coordinates, but I'm going to change it now. The blue line corresponds to perfect performance of the task. So along anywhere, any point along the blue line corresponds to total force equal 20 newtons. So if my system of two fingers varies along that line, it doesn't violate the task. I'm going to call this direction of good variability. Along the red line, any deviation from the central point lead to changes in the total force, so it violates the task. I'm going to call it bad variability. Let's now take a look at what kind of data distributions can be observed. Well, the simplest one, spherical. So all the data points form a sphere. I'm going to call it a non-synergy. By the way, if you talk to your friends and talk about synergies, and everybody will tell, oh, I know what a synergy is, and everybody will give you an example, well, locomotion is a synergy, posture is a synergy. Ask them to give you an example of a non-synergy. There will be a long silence. So here is an example of a non-synergy according to the definition that I introduced, well, a minute ago. So in this picture, the amount of variance along the good direction and the bad direction are the same, the amounts of variance. Why am I calling it a non-synergy? Well, I will try to use this thing as a pointer. Well, on average, one of the fingers is producing 10 newtons. Now imagine that in one trial, that finger produces 12 newtons. What will the other finger do? Well, since they don't co-vary, the other finger with equal probability will produce more than 10 newtons or less than 10 newtons. So the other finger with equal chance will add to the error produced by the first finger or will compensate that error. They're not working together, these two fingers. They're not looking at each other's performance. They simply decided, I'm going to produce 10 newtons, I'm going to produce 10 newtons, and they don't care. That doesn't qualify as a synergy. Now, what should be a distribution that I would call a synergy look like? It should look like that. And by the way, that's typical distributions of data points that we observe in experiments. So if you project this ellipse on the axis for the forces of individual fingers, the projections are going to be about the same for the spherical data distributions, for the gray one, and for the green one. So the individual fingers are equally noisy in these two distributions. But in one of them with covariation, the green one, all or nearly all the variance is channeled into this good variability subspace, into the direction corresponding to the blue line, and the variance along the red line is very small. So that's what you get from a synergy. You allow your elements to be noisy, but your performance is stable. In this picture, stability is something opposite to variability, but actually it is, I'll tell you a little bit later, it's same thing in real meaning of stability, like dynamic stability. All right, so, well, question is, why do I call it good variability, not irrelevant variability? That's kind of important, so let me introduce you. Now, this is the only picture where I'm going to draw a three-dimensional drawing, but I cannot do much better than that. There are two reasons why it is good to have a lot of good variability, although it seems irrelevant to the task. One of them, it allows you to perform secondary tasks within the same subspace, with the same elements. Let me, okay. Imagine that this is a cup of coffee. So I can walk around and without spilling the coffee. Well, how come my joints wobble around and my body wobble around, but I organize this variability in such a way that the orientation of the cup of coffee is always vertical, while parallel to the field of gravity. Now let's imagine that I come to a closed door like this one, and I want to open it. And my other hand is busy, I'm carrying a briefcase. What would be the strategy? One of the common strategies is this: press and push. And when you do that, you don't spill coffee, which is quite amazing, because when you press with your elbow is also involved, and shoulder, they're involved in keeping this thing vertical. If you do that, it should spill, the coffee should be spilled, and it is not, because you have a lot of good variability and your system easily moves within that space of good variability without violating the first problem. So here is a picture with, here is an illustration with force production with 3 force sensors, with 3 fingers. And there is, as you see, a pivot under one of them. Again, the task is to produce a certain value of total force. First, let's imagine that first there is no pivot. So here is the space of elemental variables with 3 forces. This is, okay, I already used the uncontrolled manifold without introducing it yet, sorry, the abbreviation UCM. Well, basically uncontrolled manifold is the subspace of good variability. These are synonyms, but I'm going to introduce it in a minute. So this triangle shows the uncontrolled manifold, or the space of good variability, where the total force is always 20 newtons. Now, what happens if I have the other task for the moment stabilization? When there is another uncontrolled manifold, when the moment is constant. Now, if I solve the problem of force production with just one perfect solution, but it happens not to be on the line that corresponds to the other uncontrolled manifold, I will not be able to perform the secondary task. I'll have to solve the task again, everything again. So here you have 2 possible performances of the first task. The red spot corresponds to a single optimal performance, which may not be exactly on the line that corresponds to moment stabilization. And this dotted ellipse corresponds to a lot of good variability. If you have a lot of good variability, chances are that within that space you can do other things, like, for example, stabilization of the moment of force. And the second one is this stability under extrinsic and intrinsic noise. In one of the very first studies using this framework, we studied how people do quick draw shooting. You know, like in Clint Eastwood movies, when you shoot without taking an aim. You shoot on the fly. It's quick draw shooting. So we had an infrared pistol, an infrared sensitive target, and we asked people to learn how to very quickly shoot at the target. They actually press the trigger without stopping the pistol, just as Clint Eastwood does. And people learn to do it very well, and they do show synergy. They show cooperation of joint rotations from trial to trial that stabilizes the relative orientation of the barrel of the pistol with the direction from the backside of the pistol to the target. Then, in one of the conditions, without giving them any more practice, we put a rubber band crossing the elbow joint. And the rubber band was at its 0 length in the initial position, so it didn't produce any force, any torque. However, as soon as they initiated the movement, which required elbow joint extension, the rubber band stretched and perturbed the whole thing. Well, it perturbed the elbow joint directly, and it perturbed everything else because everything is mechanically coupled. And I think 8 or 9 subjects out of 11 shot the target at the first trial without having any previous experience. because the perturbation introduced by the rubber band automatically was channeled into this good variability subspace, so that they perform the task perfectly well. Okay. So here is the formulation in terms of uncontrolled manifold, which is simply, I don't know, more sophisticated way of saying what I just already described for you. So the hypothesis implies that the central nervous system organizes a subspace, which we'll call an uncontrolled manifold, within the space of elemental variables. It limits variability orthogonal to it and allows more variability within it. So it's basically the same thing. It means that that most of the variance with respect to an important performance variable that you think the system stabilizes have to be within the good variability subspace. Now, uncontrolled manifold in general is not linear. So it may be curved. However, as all simple-minded people do, we always perform analysis in linear approximation, because we usually we study variance at the same phase of the movement across repetitive trials. And as a result, we assume that the variability is small in all directions. Then we linearize it. We describe how changes in elemental variables relate to changes in performance using the Jacobian of the system. And then we approximate uncontrolled manifold with the null space of the Jacobian matrix. And that's how it is computed. And then we compute variance per degree of freedom or per dimension in corresponding subspaces within the uncontrolled manifold and orthogonal to it. And if that good variance is bigger than bad one, statistically speaking, we say, okay, we guessed right. The system cares about this performance variable. It somehow organizes our elemental variables in such a way that the performance variable is stabilized. So let's, there is another definition of synergy, which my friend once took this photo. I thought it was a joke, but then I realized that was not such a joke. So it was at a conference. He asked two of his graduate students to pose with me. I frankly thought they simply liked me. But then I realized when he took the photo, no, it was staged. So two agents acting together such that the whole is greater than the sum of the parts. That's a very traditional definition of synergy. Actually, after I got this photo, first I thought, well, funny joke. But then I realized it corresponds to my definition of synergy. If you assume that a kiss is a perturbation for the neck, then having two kisses perfectly balanced on two cheeks, it stabilizes the orientation of the head and it prevents a damage to your neck. Now, a single unbalanced kiss can produce an unexpected damage to the neck. So I think this actually is a pretty good illustration. So you should always strive to be kissed simultaneously by at least two girls, two sides. Okay, so let's, since the first topic, the first kind of applied topic is going to deal with effects of fatigue on synergies, I'm going to use two objects. One of them is multi-finger force production, and the other one is multi-muscle control of posture. Kind of completely different things, but I'm going to use the same method of analysis and then introduce fatigue of one element. Okay, and see what happens. So how do we study multi-finger synergies? Well, first we should realize that fingers are not independent force generators. So if you try to wiggle one finger, other fingers will also wiggle. Okay? This is partly due to purely mechanical peripheral links, but it's actually 5% of the effect. Partly due to the multi-tendon, multi-digit muscles, and partly due to the overlapping cortical projections of individual digits, which we think is 90% of the effect. Because it's all these enslaving effects change very, very quickly with specialized training and in special situations, while periphery cannot change that quickly, obviously. So, since finger forces are non-independent by design, then we expect that in the space of finger forces, independently of the task, the data distribution is not going to be spherical. It's going to be elongated, elliptical in some direction. So by pure chance, this ellipse, which is simply part of the design of the system, may coincide with our uncontrolled manifold or be orthogonal to it. So in order to get rid of that problem, we record forces of individual fingers, but we then compute hypothetical commands to fingers that in general can be changed by the brain one at a time. So we have this picture in mind. We call these elemental variables of this analysis force modes. And the idea is that the controller sends signals that correspond to desired involvement of individual digits. But each of those commands projects on forces produced by each of the digits with different degrees, with different, so thickness of the lines more or less correspond to the amount of force being projected on each individual digit. Now forget about force deficit, because in this picture it makes, it's not very interesting. The important thing is that we assume that this mapping is linear, and it is indeed, experiments show that it's quite linear over a very large range of forces in pseudostatic tasks, in relatively slowly tasks. So we assume that finger forces are consequences of these modes multiplied by what we call the enslaving matrix, which I showed in the previous slides. So now you can invert the enslaving matrix, you can record forces and compute modes. And that's what we do. So we study variance across trials in the space of modes, not in the space of forces. So by definition, multi-finger synergy, I'm just repeating the definition which I showed before, but now translating for fingers. It's a task-specific correlation of finger modes across trials with the purpose to stabilize total force or total moment of force. That's what fingers usually do when they act together. So what can happen with fatigue of a single digit? Several studies showed that if you fatigue one element of a multi-element system, the system doesn't suffer too much. Its performance remains more or less unchanged. There were several studies about multi-joint movement done by Julie Cotet in the University of Montreal and in McGill also. And they showed that you can fatigue, for example, the elbow joint. Well, when you fatigue a joint, the joint becomes, well, first of all, it becomes weak, obviously, the muscles, by definition. Fatigue leads to a drop in force. But it also becomes noisy. So variability of muscles goes up. So if you fatigue elbow joint and then you give your subject an elbow task, the subject is going to be less accurate. However, if you fatigue elbow joint and you give the subject a whole arm task, the accuracy is more or less preserved. So we decided to study it using the idea of synergies. What happens if you fatigue only one finger? There are actually two possible outcomes that we expected. Now, one we call the so-called weak link hypothesis. Imagine that you are